struggles, and as of this year, a closure to this long-term project, and some open questions that have come from it, and just a general theory that I have no clue how to proceed or begin, but um, I hope it's interesting. Okay, so motivation, this beautiful work by Dürer. It's actually a book, one of my favorite book that I actually physically found of his that's in print. It's called The Painter's Manual. And in this book, he is, Dürer's a Renaissance superstar about 500 years ago, but he draws as a painter, sculptor, lithographs, and at the same time, he's thinking of it from an architectural perspective and as a mathematics perspective. All of these lines are blended together. And his main struggle in this one piece is how do you depict a three-dimensional object like you see right here, this object, right? How do you depict this in 3D without distortion? And of course, you're drawing it on 2D paper, so you're distorting it. There's this line to infinity, right? All these things are converging, but he wants it without distortion, and you can't do that. Like dimension reduction is killing some data. And so his solution is actually cutting and unfolding, where you lose the adjacency issues of that 3D object in some sense, but you have no geometric distortion at all because you're laying it flat on the plane. And given one of these unfolded nets, you can recover the object by gluing the edges back together again and recover this 3D polyhedron. Great. So the question that was asked in the 80s was, is this always possible? So let me give you an example. Here's a soccer ball, a polyhedral version of a soccer ball. And the rules of the game are as follows. One, you can cut along any of the edges you want, but only along the edges. That's rule number one. Rule number two, it has to stay flat. So you have to kill all the curvature at all the vertices. Rule number three, it has to stay connected. Of course, I can kill all the edges and you win because it stays flat. Or I can cut none of the edges and it stays connected. But is there a collection of edges you can cut that gives you the beauty of both connected and laying flat? And let's think about this just for a second. If you take any spanning tree on this one skeleton, if you take any spanning tree on this one skeleton, you just need to get to every vertex. If you draw a spanning tree, I claim that you win. Why? Because since it's a spanning tree, it touches all the vertices and your knife cuts to all the vertices and it kills the curvature at that point and it opens up. And since it's a tree and not a cycle, then you've never disconnected the graph into pieces. It stays connected on the other side. So any spanning tree works. So here's one example of a spanning tree. You can cut along the spanning tree on this one skeleton and you get this unfolding. Great, this is exactly what we want. But this is another spanning tree right here that also gives you the unfolding. It unfolds flat and it's connected. But this is a better answer than this answer. And this is the last and the most intricate part of Dürer's piece that he notices. You don't want these objects to overlap when they unfold. And if they don't overlap, like this is called a net. But a generic spanning tree, anything that you can do, is called an unfolding. So what we're looking for is not just any unfolding, but we're actually looking for a very special unfoldings that are nets. Is this always possible? Okay, great. Here's some beautiful, I think Archimedean solids, some other beautiful, like truncated Polyhedra, some really beautiful pictures, even the soccer ball on the left. And you see that if I just randomly or kind of lazily cut these edges, you will end up with small amounts of overlap or actually a decent amount of overlap, depending on how these things are cut. So you have to be careful when this is done. And for a generic one, here's what Joe was able to just create a generic polyhedron, like points in R3, take the convex hull, take a cut on one of these spanning trees, you get lots of overlap, right? So you have to be, just the notion of a greedy algorithm won't necessarily work easily. And Eric Demain and a handful of others showed that, by the way, if you have non-convex polyhedra, things get more dangerous. There are examples that it will never work, that no matter which spanning tree you pick, you'll always get problems, mostly because you have these high curvatures because of these reflex corners. And they're going to add up more than 360 if you're not careful in terms of the way they flap. So these examples are guaranteed to fail, that no matter what spanning tree you pick, it'll always fail. And so here is this motivating question for the talk, which is, does each convex polyhedron always have at least one net? Out of the collection of spanning trees, given it has a handful of finite number of edges, you know that it's going to have a finite number of spanning tree. Does at least one of the spanning tree have a beautiful net that works? Questions for me before I move ahead? And if you have any questions, just please jump in. So let me tell you the state of the art that I know of this problem. The state of the art is even for a tetrahedron, we have to be careful. I found this incredible. I mean, four triangles glued together. Of course, this is not a regular tetrahedron, right? This is a kind of a squished tetrahedron. You see the two triangular faces in the front and the two triangular ones in the back. And if I cut this inappropriately, you get overlap. So you need to be careful about how you do these things. And even the simplest of all polytopes get you in trouble. The Platonic solids, they're so beautiful that they do have answers. Like there is a way to unfold each one. So they work. Great, wonderful, check. The box works for the Platonic solids. And I was in this talk that in about 15 years ago at CCCG in Montreal, I believe, in McGill, that has motivated this entire talk for me. And here's the paper that was presented by Horiyama and Soji. They said, edge unfoldings of Platonic solids never overlap. So let me translate that. What they showed is that not only is there an unfolding, like a net for the Platonic solids, like we showed here, but every unfolding is a net. In other words, you could be as lazy as you want, and every spanning tree you could imagine will work. And so for the cube, there are 11 distinct unfoldings. Each one of them, right here, I'm going to show you the 11 right here, and they're all nets. None of the flaps overlap. And by Poincare duality, you could show that the octahedron also has 11 unfoldings. That also, perfect, all the unfoldings are nets. Then we have the dodecahedron and the icosahedron. They're not 11. Can anybody guess the number of unfoldings they have? Any thoughts? Okay, good. 43,380 unfoldings, and they're all distinct up to symmetry, right? And all of them are nets. And this paper that I was listening to when I was at CCCG was showing that they computed all of these unfoldings and checked it. And to me as a mathematician, this is incredibly furious, right? Like, why is this working? What is it about the Platonic solids that makes it that every unfolding happens to be a net rather than just a computational check? And of course, the paper was not just checking the 43,380 and the 11 and all the different versions, but they actually checked it elegantly and quickly, right? That they had kind of data structures that did it correctly. So I don't want to dishonor them for their work. But as a mathematician, this is not exciting to me at all. Like, I have no interest in the fact that this thing is working by just brute analysis. I want to know why it's working. And the unsolved question that I will leave with you today is, even now, I don't know why in general it works. So given some structure, can you guarantee that all of their unfoldings are going to be nets? And I don't know what the sufficient conditions are. There are some simple necessary conditions. I just don't know. But let me tell you how I approach this thing. I just cheated. We just switch gears, right? We're like, okay, that 3D case in general, the gods are thinking about this thing. Like, if Eric Demain and a few other people are really interested in focusing on this thing, I don't want to focus on this. This is not my specialty, but I want to play with this idea of like cutting and unfolding and always working is really interesting. So in mathematics, of course, we just change the 3D to ND and you could just play this game. But in ND, things get more difficult in general unless I just focus on cubes. So the entire talk in the first part of it is just thinking about cubical issues. So here's the Schlegel diagram of the 4D cube. Instead of cutting edges, I want to instead of cutting 1D edges in a 3D polyhedron, I want to cut 2D faces in a 4D polytope, right? And these two-dimensional drops are called ridges. One-dimensional drop, codimension 1 are called facets, and two-dimensional drops from the top are called ridges. So you have these main chambers, these facets, and you have ridges that glue them. So for a polyhedron, the ridges are edges, or we just call them edges. But in general, in higher dimensions, these are called ridges. And so what I'm trying to do is I'm trying to cut along the ridges and unfold it. So one unfolding is this, right? This is an unfolding of the 4D cube. It looks just like the unfolding of the 3D cube with that extra dimensional kick. And you could imagine the six flaps go around, and then the longer one of the cross format kind of fits and then closes to the eighth cube that is making up the 4D cube. This shows up, by the way, in the work of Dali, right? It's this beautiful work called The Crucifixion. It's also called, I think, Hypercubus, or I forgot exactly the other name that he also called this thing. But around this time,
Hypercubus.
I'm sorry.
Corpus hypercubus.
Oh, thank you, Gunther. Um, yeah, but around this time period in the 20s to the 1950s, there's these notions of religion and space and time and fourth dimension and kind of what these things mean. And there's a big struggle by artists thinking about many of these things. Sol LeWitt, another artist who I adore, thought about all the unfoldings of the 4D cube. So let me frame the entire talk today for the next half an hour as follows. So let me move my little mouse thing out of the way so I can see a little bit more clear. We look at the 3D case, the 4D case, and the ND case for regular polytopes. All the objects that they're tiled by, the facets have to be identical, and then they have to be glued identically. So there's this kind of simply transitive action, group action that takes anything to anything else. Basically, whenever you're standing somewhere, you're lost as to where you are. Everything looks exactly the same. And there are 5 things in the 3D world, the Platonic solids. There's 6 things in the 4D world, and there are only 3 objects that exist in these worlds that generalize into all dimensions. So there's the cubes that are n dimensions, there's the dual to the cubes, the octahedra, and there's the simplex and the dual to the simplex, which is itself. That's it. Those are the only 3 things that generalize in all dimensions. And there are these kind of like exceptional 5 pieces that are floating around over here. So what I want to ask the question is, do all of these things have a property? The property is the all net property. We just came up with it. Actually, Joe Rourke recommended this thing because it's like Michael Jordan making the shot and you see like nothing but net, and the basket goes in and all you touch is the net, is that every unfolding is a net. You just are lazy and cutting in any spanning tree or any spanning ridge graph, you could think of it in the higher dimensional thing, and you just keep getting nets, like there's no overlap. Which of these things have this property? So let's take a look. We know this is all true according to the paper. They proof by exhaustion, right? We have that down. Excellent. And what we want to do is look at the cubes, look at the simplices, look at the octahedra, and look at the exceptional cases. That's what the talk's going to be about. Questions before I move ahead?
Are you going to talk about, are you going to also talk about a proof for the 3-dimensional case, or?
I will talk about the proof for the no, I'm going to talk about everything except these 2 cases, Adam. So I'll talk about the proof of these 3. Okay, so these 2 I've kind of ignored for now. But partly because they're still so exceptional, even the way we handled this was weird, right? So let's take a look at the cube, and most of the talk is going to be on the cube. I'm going to hand wave a lot of the other things that's written down, but the cube is the most interesting to me, and it's the most beautiful. So here are some unfoldings of the 4D cube into 3D. Do you remember there were 11 unfoldings of the 3D cube into 2D, and all of them were nets? So there are 261 unfoldings of the 4D cube into 3 dimensions. And this is one of the things that Sol LeWitt was kind of worried about and really cared about in some of his sculptures. Great. Okay. All of these happen to be nets. That's surprising. Okay. That's cool. That's interesting. So let's take a look about what's going on. So here's the way I want to think about this thing, because to draw these things and to capture this in higher dimensions is silly in a direct visual correlation. So what I want to do is you just look at its dual picture of what's interesting. So given this unfolding, you have a cube. You look at its one. You look at the dual of the one skeleton, right? You look at the dual of this object. You look at the one skeleton of that dual, and then you can draw it like this. And what this is a complete graph of 2n vertices. 2n because you have 2n facets, and complete graph because everything touches everything else, except for one small rule. The antipodal vertices don't touch each other, right? So you just delete those antipodal ones because the bottom facet of a cube does not touch the top facet, right? This has a name. It's called a Roberts graph. It's called a 2n and Turan graph. It's a very famous graph that shows up in many different pieces. But this is what I'm interested in so far, to look at this. And what I'm going to be doing is, if you have an unfolding then that means it corresponds to this corresponds to a spanning tree on this graph. Because the unfolding itself needs to be connected and it itself can't have cycles, right? So all I'm doing is giving Adam this following simple homework problem. I give him like a 2n Roberts graph, right? 2n nodes, complete graph with the diagonals, the antipodal diagonals removed. I give him a thick red marker and I said, draw any tree you wish on this thing. So he draws an arbitrary tree. We know that that drawing that Adam has done corresponds to an unfolding because of what I've just shown you in this picture. So my question is that unfolding a net? Actually, more interestingly, or more even simply, is like, what the heck is the unfolding? Like, how do I take the combinatorial data of me drawing something over here, which is just a tree, into a geometric data of actually talking about coordinates and how these flaps unfold in the n-1 dimensional space? So let's take a look. I am looking at spanning trees on my Roberts graph, and it turns out, for example, this one, they have 8 nodes. They all correspond to geometric unfoldings of these cubes, and this is the correspondence. So how did I go from the top to the bottom? Well, you can go from the top to the bottom in a brutal way. You could just kind of figure it out and redraw the whole thing, but is there an algorithm to do it, and how can it help us out? I want to show you that there is one, and it's really elegant. So given any of the spanning trees, you should be able to draw an unfolding. I want to then check if these unfoldings are nets. Okay, so the method we do it to go from the top to the bottom, the algorithm, I want to show you the one-dimensional example that's below, the 3D to 2D first. So roughly what I'm doing is that given any one of these creatures, if you go back, forgive me for switching back and forth, but if you go back to one of these drawings, what I want to do is I want to kind of pick one as my base, as my home base. And the reason I say that is this thing has 2 times 4 nodes, so it's really in 4D. But when I'm unfolding it, I'm only unfolding it in 3 dimensions, right? So I have 3 coordinates I need to worry about. And notice you never have the antipodal one, right? That's never available to you. So the way I start thinking about it is, well, you pick any direction you want in your Roberts graph, and you give it some random direction in that one dimension less. So you just call it the x1 unfolding direction. The moment you pick to be this s1, its antipodal one over here is going to be negative x1. That's what those opposite directions are going to be on the Roberts graph. If this is x1, that's negative x1. And then just call the next direction you want x2. Make that go up. Make this go to the right. Then its antipodal one is going to be negative x2. And there's, by the way, a full Coxeter group of type BN, beautiful symmetry behind the scenes, that you could randomly pick any direction to be anything, as long as you pick the antipodal direction to be its opposite. And it's going to give you the same unfolding up to isometry and reflections and rotations in n-1 space. And this is exactly what I do in 3D, right? You have these choices here. Remember, there's never a picture that will take my graph from here all the way opposite. So I could just ignore the opposite ones, the antipodal ones, but just pick the directions you want, right, left, in, out, whatever you want, and then choose the antipodal ones to be just the opposite ones. Great. Once you do that, my entire game is going to be rolling the cube. I am going to be unfolding by rolling and stamping, like literally imagine an ink, and I'm just stamping these cubes in 1 dimension less as I do this. So as an example, this is the notion of starting at, say, 1 star, 3 star, and as I rotate, I'm stamping, this edge gets stamped down, and it gets rotated and changed. So the 1 is now moved into the 3-star position. In higher dimensions, the same thing. Anytime you have one of these edges and you perform this rotation, the rotation does something interesting for a cube, which is for an n cube, if you rotate it and stamp it in n-1 dimensional space, only 2 of those n dimensions are actually moving. The other n-2 dimensions are they're kind of basically fixed on the sides, spinning around because you're stamping in that direction. You take the direction where you're at and the direction where you want to go, and it's only movement in those 2 directions. So given this position of 1 and 3 star, if I decide to rotate the 1 and 3 star, I'm at the 1 position, I'm looking at it towards the 3-star direction, and I'm moving in that direction, all that means is the 2 star, the 5, the 4, all their duals just stay around. Nothing happens to that cube except the 1 and the 3 star just rotate and revolve in those two possible directions. So given that property of the cube, we have this lemma, and it's a really simple lemma. And the lemma says, in the unfolding along some path of the spanning tree. So remember, Adam's drawn this spanning tree for me, and I don't need the whole spanning tree. I'm just going to choose some path of a spanning tree, right? So just any path of that spanning tree that he has, if you go in direction X, if somehow as I'm stamping, if I use direction X in my movement, then direction negative X will never be used along the path unfolding. You could think of this as no U-turns. If I'm going in a possible direction in the X direction, then you can go to the Y direction, you can go to the Z direction, you can go to any direction you want to, but you will never go to the negative X direction again. You will continue, if you want, to go in the forward X direction, but now in the negative X direction. Why is this true? The proof is completely silly. It's this picture. The proof simply says, okay, imagine you're at this spot. This is the spot that has a stamp, and you're stamped on the n-1 dimensional hyperplane. Here's the X direction. Okay. So if I'm going to go in this direction, remember what that means is I take these four pieces and I rotate those 4 pieces, which means this point that has already been stamped is now moved over here, right? This point that's already been stamped is moved over here. That facet has now been used. I can't use that facet again because you've stamped it on the plane. And this facet over here has been moved down over here. This X now comes down over here. And here's your new picture. The only way you can ever go and pull in the negative X direction, remember, there are all these different directions with all these different grid lines. The only way you can go in the negative X direction is to rotate backwards along that same rectangle. And you can't rotate backwards because this stamp has been used. So once you've used it, you can't go back and visit it again. You could do a lot of other X's. You could do X's all you want to, but you could never do a negative X because it's been used. And so that's the silly little proof. And that's all the lemma you need to guarantee this theorem. Every ridge unfolding of an n cube yields a net. That's it. Which means no matter how you cut it, going back to Adam's question about the 3D case, like all the 11, it's going to work for the 11, it's going to work for the 261, it's going to work for everything. Why? Well, because if I never have a U-turn, if I never can come back to where I start from, that means you can never have an overlap. So proof by contradiction. If you have an overlap, then it must be somehow you came back to the same point by a U-turn, but we can't have U-turns, so you can't have overlaps, and that's it, we win. That's it. And so it's a straightforward thing, which means that the two cases are guaranteed, not just distinct, they're guaranteed to be nets. Everything here, guaranteed to be nets, right? And these numbers, by the way, I have no clue. They're just the online integer sequence superstar encyclopedia. But it's amazing that this is always going to be holding true for cubes. And so for us, we can solve this entire column by saying they all satisfy the all-net property. Any questions so far? This cube case is interesting to me. Let me show you, one, a little algorithm, and two, some unsolved questions that have come up here in this cube case. So the algorithm is, we can actually, I never told you if Adam gave me this drawing, how to actually show the unfolding. But the way to do it, I'm going to do this really quickly, but we can sit around and talk about this longer. It's actually written down in a paper, which is that the moment I take one of these edges that it's touching here, what I'm going to do is I'm going to go in this direction. And imagine this one is almost like the jaws of a shark. And the shark is going to pull whatever is touching it, and it's going to eat it. So it's going to pull this 1 3-star edge towards it. And as it pulls it, the only way you can pull this towards it is you're going to rotate those 4 things. You're going to stamp so that this edge gets pulled in, and the 3-star is now the new stamp, right? So I'm moving along that ridge. This 1 3-star is a ridge, and I'm moving from my facet 1 to my facet 3-star along that ridge, and I'm stamping it. So if you do that, remember, we've decided that this is in the X1 direction, So as I do this, I just put an X1 stamp on it. So this cube is literally getting stamped in the X1 direction. Okay, so I do that rotation. Once I do that spin move, after I spin these 2 nodes, this is what I get. And notice 2 and 2-star haven't moved, right? They have no need to move because I'm only spinning the cube this way. So the 2 facets on the side just sit around. They don't do anything. I mean, clearly they spin and rotate, but they don't move in terms of the planes that they're on. So now I'm done with this. Notice that this is colored white because that facet has now been stamped. This is colored white because that's the stamp on the floor, but it's now ready to take the 1 star. So now it pulls in this direction, but that direction is X1 again. So you just pull in the direction, X1 gets stamped, then I rotate these 4 things, and you get this after you do the rotation. Great. And now you see the next one to get pulled is up here into this position. So you pull that, and you keep pulling it until this bottom vertex, just basically the bottom nodes, eats your entire path. And as it's eating this path, these things are spinning. And as it's spinning, you stamp in these different, this cheat sheet that you've used to talk about the geometry of the direction you want to go. And you could just unfold this. So this is the unfolding that you get. This is the net that you get for the spanning tree. And you could do the same thing for the 3D case. Here is again a path, which happens to be a spanning tree. Here's my code for what I've decided the directions have to be. You could pick any directions you want to. And you could just follow along and pull this thing and then stamp away. And you get this unfolding, which we proved is a net for this path. And if you don't have a path, if you have a tree, by the way, then you could just basically unfold along each of the path, each of the subpaths within it, and it'll give you that branching and give you that tree structure for your unfolding. Okay, great. So there's an algorithm to do it. Here's a question that that was inspired by this picture, right? I'm trying to ship these boxes to Adam in New York, right? Here I am in San Diego. I need to ship these cubes. I'm shipping these unfoldings. So if you notice the kind of boxes I want to get, this is a 4x3 box that I want to ship it in. And there's a 4x3 box over here. They're all 4x3 boxes except one 5x2 box. Well, that's interesting, right? So I'm trying to ship this over here, and most of these things fit into this 4x3 kind of thing, except there's this one 5x2 kind of an object. In higher dimensions, you notice that there's these 6x2x2, 5x3x2, 4x4x2, right? These 4 different kind of 3D boxes that my unfolded nets are going to be to ship in. And I'm going to define something called a cube partition. An n cube partition is simply an integer partition of 3n minus 2 into n minus 1 parts, where each part is at least 2. All that means is you have n minus 1 blanks. Make sure each one of those things is at least 2, and you have a total of 3n minus 1 to kind of distribute over there, right? Roughly what that means is you can choose it to be 3, 3, 3, 3, 3, 3, 3 all the way, and you have to have one of a 4. Right? At the end of the day, if you kind of add that up, you have to have a 1 of a 4, which means it's kind of basically going to look like a cubical box, like a big, nice, beautiful cube. Like the one to the right over here, you see it's a 4, 3, 3 on the right side. This almost looks like a beautiful cube. The other end of the partition could be a 2, 2, 2, 2, 2, 2, 2 with like an n minus something, like an n minus 2 or something like that left over. So you could have this long rectangular box, right? Like almost like a tube that you can ship as n increases in size. Those are the kind of partitions that you have, and you have a whole distribution of these longer ones and more of these fatter ones. And you can show that any of the unfolding can fit into one of these boxes. And you can also show that given a box, I can find an unfolding that fits into it. So it's both, right? Like, so any size box, as long as it satisfies this kind of cube partition condition that I have, Adam says, here's the kind of box I want you to ship it in. I can find an unfolding that fits perfectly into it. Or given any one of these unfoldings, they're all going to fit into one of these boxes, guaranteed. And this is what I don't know. I just don't know how the distribution looks like for these boxes. Like in the previous example, most of them were kind of a 4x3 and one was a 5x2. Is it more common to have these kind of distributions in my nets? Like, are cubes more present? Or is it more common to have these skinny, like how do they, doesn't feel like a normal distribution size to me. I just have no clue how these boxes are looking. We know they're nets, but what kind of nets do they form in terms of their geometry? I don't know. That's interesting to me. And I'm going to pause here. Any questions? Okay, that's the brunt of the talk.
Yes, I have a question.
Oh, please, Gunther. Yeah, please.
Yes. So does it, I mean, this, not going back, does it mean if you take 2 adjacent cubes in this picture
Yes.
and you look at the hyperplane that separates them, you get 2 connected pieces? Is that somehow related
when you say 2 adjacent cubes in this picture, you mean this particular picture right here on this thing?
in the unfolding,
Oh, in the unfold. Oh, so you've unfolded the cube into one dimension less?
Yes.
And then when you say two adjacent, what's the next one? Another unfolding?
No. The cubes are adjacent. I mean, there's a spanning tree, and maybe actually, is it always a tree? That's another thing. That apparently you don't get extra touchings.
That's right. That's
Yes.
right. In your unfolding, you'll
So
always.
one thing is that if you have like an edge of the tree, that means that you have two adjacent cubes in the
Yes,
unfolding.
yes, yes. You mean two
And
adjacent
now
n minus
in
one dimensional cubes. That's
yeah,
right.
so in that minus one dimensional space, you can look at the hyperplane that where it's n minus two dimensional.
Yes, yes,
In this
yes.
case, it would be a plane, and it
Yes.
separates it into two connected.
Yes, that's exactly correct. Like because you don't, I mean, like if you look, that's right. Like if you look at this little hyperplane here, on this side it's touching three faces, three squares.
Yes.
On this side it's only touching one square, right? But because it's the boundary of one of the, but at the end of the day, that's right. It separates into these two pieces all the time.
Yeah.
Because there's no U-turn, everything
Okay.
kind of keeps branching out, right? So once you cross a hyperplane, you can't cross back.
Okay.
Something else. But it's a tree. So it's so if you remove it.
It's saying that you take them into adjacent.
Okay. Other questions? Okay, I'm gonna move ahead. So that's the cube. There's a few other pretty questions related to it. I have questions about rigidity. There are a lot of really interesting questions about how this unfolding structures, because exactly Gunther's argument about it crossing a hyperplane, it can't cross back, it always does a separation. There's beauty to it. The simplex case, let's focus on this thing. I'm not going to say too much about this, only because here is how these unfoldings happen. You just look at it based on reflections. The reason cubes, also, of course, unfoldings are based on reflections. The reason cubes were so pretty was because geometry became combinatorics, right? Because Rn is tiled by cubes, and Rn minus 1 is also tiled by cubes. So you could just translate your cubical geometry, which we never talked about 90 degrees or anything like that, into just lattice coordinates. And that's all I'm doing. I'm placing these as lattice coordinates, and you get this beautiful geometry based on just the combinatorial data behind the scenes. It's not the case for the simplex. The tetrahedron is unfolded and can tile the plane because the equilateral triangle tiles the plane, but that's it. The tetrahedron that's in 3 dimensions does not tile 3 space, much less the 4 simplex tile 4 space. So we have to kind of be careful in terms of using a little bit of linear algebra and thinking about how these tilings are unfolding and keep track of whether there's an overlap. And we could show, without too much difficulty, it's not that difficult, to show that all of these things unfold easily. It's just, there's not enough tetrahedra, or there's not enough n-1 simplices to really get you into trouble of unfolding things. That changes, by the way, when we get to octahedra. Like these octahedra, it's not just a tetrahedron. You have a lot more triangles, right? For the tetrahedron, there are only 4 triangles. For the octahedron, there are 8 triangles. And because there's so many of them, now you might start getting overlap if you're not careful. So let's take a look at the octahedron. So here's the unfolding of the orthoplex. That's the octahedron of n dimensions, the dual to the n cube. And there are 11 of them. And anyone have a guess as to the number of unfoldings of the 4D orthoplex, the 4D octahedron? Remember, there are 11 unfoldings of the cube and 11 unfoldings of the octahedron, and there are 261 unfoldings of the 4D cube. Anyone has a guess as to how many unfoldings of the 4D octahedron there are, the 4D orthoplex? You can guess in your minds if you want. The answer is 110,000, right? So I thought it was in the, like, kind of in the 200 property, right? You're kind of doing duality. Okay, maybe it's not exactly the same thing. By the way, Poincare duality is not working at this point because you're cutting at a wrong dimension. The 3 and the 1 and the 2 are working out for the 3D case, but not for the 4 and the 1 and the 3. So it doesn't, the way you want to count does not work so nicely anymore. It no longer follows the beauty of the cubes. So you have all of these distinct unfoldings. And there's the theorem. We proved that every unfolding of the 4 orthoplex yields a net. So all of these are going to yield a net. And the proof, let me show you the proof a little bit. We take, of course, the orthoplex that we want to do it, and we give it some coordinate system. the dual of this orthoplex is actually what we are keeping track of, and the dual of the orthoplex is a cube. So the geometry is over here and what I need to do, but in terms of keeping track of the dual of how I'm going to unfold it, I'm just following the cube. So what you end up with is as you walk along this way is you could just basically think of moving from 101 to 100 to 110. That basically you're just stamping this object. These are exactly the gray codes. Like there's a way to keep track of this thing as to walking along the vertices of cubes. Mathematicians and computer scientists have been thinking about this for a long time because cubes encode so much data and keeping track of them. So we have this gray code. This gray code, you could write it like this if you want to talk about the unfolding, but you could also write it like this notion of 323 is a way of saying like which coordinate is actually changing information. So to go from 101 to 100, it's 3 that actually has changed. So you can keep track of this information this way. And then here's the lemma. We have to be a little careful, but let D denote the distance between the centroids of two n-1 simplicial facets of the orthoplex in an unfolding. So imagine, I'm looking at almost worst case scenarios. Think about these centroids, think about the unfoldings. And then if D is less than this framing of this number, the facets must intersect that they represent. And if D is bigger than this, the facets cannot intersect. So remember, I can't do this combinatorial trick anymore. I'm just keeping track of the centroids of these simplicial facets as I'm opening it. If the distance becomes really close, you have no choice. Somehow the facets are going to be colliding. Remember, these are weird facets, by the way, right? Because these aren't circles. These are simplices. But this guarantees that somehow, no matter how you put it, if they're close enough, they're going to collide. But if they're far enough, you're going to be fine. And then we're able to show for n greater than 4, there are unfoldings of the orthoplex that are not nets. Which means that for the 3D case that Adam asked for, all the 11 unfoldings are nets. And the proof is there because you could use this D argument to actually get it. And for the 4D case, we can show it using kind of a subtle, cool combinatorial framing. But greater than 4D, you will always have orthoplex unfoldings that fail. And here they are. These are examples in the 5D case. This is the gray code. You can actually sit down, write the dual to what this is going to look like, and follow along in the dual to what the chambers are going to be. And you will see that this will give you an unfolding. The very first facet and the very last facet, these, by the way, are the hyperplane switches between them, are going to give you overlap. This is the 6D case. This is the 7 and 8D case. And this is the 9+ dimensional case. And what's interesting to me is the number of simplices needed to give you unfoldings is becoming less and less. In other words, with small amounts of simplices, you're already getting problems. And so for the 5D case, these aren't, by the way, these are not optimal or ideal. These are just examples we found. But I don't know what's happening in this case. Like, I don't know why we can't find a smaller chain. These are chains, by the way. Why I can't find a smaller chain, a smaller path in my orthoplex that gives me collisions. I need to have a path this long, at least from what we checked, to give it. But as you get to higher enough dimensions, it's like 1, 2, 3, 4, 5, 6, 7, 8. It's like 10 simplices already in your unfolding. It's going to give you collisions or in your pieces. So don't know. I don't know what's happening. I really don't understand. These are just elegant things. They're tiled by simplices. But we're getting problems. So in some sense, that works and that doesn't. Okay. And so the last part of the talk, the last few minutes, I just want to close with this. The first two, I'm not going to reference as Adam wanted to possibly have a proof of that. We never even looked at that and considered it. But I want to look at these 3 exceptional key pieces. Before I do that, though, I do want to just show this to you. If you go to my website, Sam Zhang, he got his doctorate on design at CU Boulder. And he developed this beautiful graphic applet that you can just go and play with. You draw that spanning tree that I was talking about earlier for both the cube, the simplex, and the orthoplex, and it'll give you the unfolding. It'll give you the net. It's really elegant, right? So it's a kind of a wonderful, fun little tool to play with what's going on. And those are the cases that work. Just to go back, yeah. And you can actually see it right here if you click on that button. Let me move ahead to the next slide.
So Sam doesn't know a lot of math, and
he's what's the right way of saying it? I don't know exactly which department. It's almost like applied math / graphic design. Like kind of an intersection, but I mean, he learned this, we taught it, and he learned this thing really quickly, right? But he knew enough to understand what we're talking to do, which is exactly some of the things that Gunther was saying. Like, there's this hyperplane, right? You do a reflection, it's linear algebra that's just capturing it. We're guaranteeing it's going to work, and he's just visualizing it. So,
Okay, I'm just guessing that the standard design student who never studied calculus.
oh yeah,
would have
that's
a hard
exactly
time
right.
with
That's
it.
right. Forgive me. Yeah. He got his doctorate on this, and he's done. I mean, he does kind of data analysis and like very high level, dimensional work. So when I say design, I mean design with a capital D, maybe, Adam. So let's close with these three exceptional cases, and then we're done for today. So the three exceptional cases, let me first of all show you this amazing result by Birkenhout and Parker. This paper came out, I believe, in 1993 or 1994. They used they used abstract algebra and just notions of symmetry to count the number of unfoldings. They're not interested in nets. They actually, in their papers, use the word net inappropriately. They actually should say unfoldings. They're counting the number of unfoldings, and so they were able to find that there are 11 unfoldings for the cube, the 11 unfoldings for the orthoplex, all of those kind of numbers, the 110,000. They came up with those numbers. Let me show you the number of unfoldings. This is the 24 cell. It's made up of 24 octahedra glued together. This is the 120 cell. He's stretching. This is a 120 dodecahedra glued together. And the last one is the 24 cell. The first one is the 600 cell. It's 600 tetrahedra glued together. So those are the three things, and they were able to find out the number of unfoldings. Here they are. It's not 110,000. It's not 11 or some ridiculous. Look at this number, 2 to the 188. It's like the number of atoms in the universe. And then you multiply it by 3 to the 1. I mean, it's just, these numbers it's incredible, right? And then here's the second one. And amazingly, this is interesting. This might work, right? I mean, it's not this crazy. 2 to the 19, that's something we can do. And multiplying by this number, and like, I don't know why that 347 is there, but whatever. They did this work. It's a beautiful result. I think it's in discrete mathematics. So they were able to show these are the unfoldings, the number of unfoldings. And it feels like, listen, one of these things has to have overlap. I mean, the chance that all of those are nets, I mean, there's so many of them, right? You got to unfold all of those 600 tetrahedra in 3 space.
So Satyan, is
Yes,
this
please.
up to symmetry?
I'm sorry, my friend.
Up to symmetry or
Up to symmetry. Yes. Up to symmetry. That's why you have these weird numbers like 347. Up to symmetry. Yeah. Like the 11 we'd get for the cube is up to symmetry, right? If you kept track and colored these things, you'd have a lot more. But up to reflections, rotations, and up to symmetry, you have this. So here's the unfoldings for the 600 cell. It actually turns out in a small little area, you could actually think of it, the dual to the 600 cell is the 120 cell, which is tiled by dodecahedra. Even in one dodecahedral chamber in the dual, if you choose these as your nodes, which correspond to simplices, and unfold those simplices, you get overlap. Right here, there's an overlap between the first and the last. So in very small, compact pieces, you don't even have to walk around too far. You're going to get in trouble. So the 600 cell definitely fails. For the 120 cell, it also fails. You have to walk a little bit further, but there are failures of what's going on. Now, a very fair question could be is, how many of these are failing? Like, what's the distribution of success to failure? No idea. That was not my interest. That's beyond the scope of my powers. I just wanted to know if it worked. I do know there are unfoldings that succeed, and I also know there are unfoldings that fail. So it fails the all-net property, but that's all I know. I mean, that's the edge of the knowledge that I have. And this is the hardest result, and we just found this out just almost by trial and error a few months ago, which is you can actually glue this. These are octahedra, and there are 24 octahedra. You can actually unfold the octahedra properly. You have to be careful. The geometry here really does matter, because it's not just a gluing of any octahedra. You have to glue it as this is glued here. But you do get collision. If I glue one extra one that's red, the next one here, you would get a collision. So there are failures in the 24 cell. So the state of the art is this. That's the state of the art. And I want to close this talk by simply saying, what is the general property? I mean, like, what's going on? Like, what is it that's making some of these work? Or if somebody gives you a polytope, is there a necessary or sufficient conditions that can guarantee whether it has an all-net property or not? What do these have in their bones that make it work? And does it change after a certain dimension? Like to me, this is incredibly curious. It works for 3D and 4D, and it just fails for 5D. That's very surprising. I just assumed these would work, and there might be some weird exceptional cases, but this is surprising for every dimension for 5 and greater. So I just want to stop there and just say thank you for your time. Really appreciate it.